So here we want to test a claim that the average heart rate of ICU patients is at most 95 beats per minute, significance level of 5%. Pick the null and alternative hypothesis. All right, so let's grab a screenshot and scribble on this. Get to the proper new page. All right, so this is the claim we have to go on. So we got to puzzle out some things about it first. So what's the population here, right? There's a sample talked about down below, but what's the population? So the population here is anybody that goes to the ICU. So I'm going to do a little more than was asked for here, just to help clarify this. Any person who goes to the ICU, intensive care unit, by the way. And the parameter I'm trying to measure, is it a mean or a proportion here? It's a mean, so I'm going to give it the letter mu, and that would be the average heart rate, not the heart rate of an individual person. Those will vary greatly, but average heart rate. So that would be beats per minute of somebody in the ICU. So the claim is at most, and let's see, I just got ding-donged. What does that mean? We have a new attendee, or someone just jumped in that wasn't there before, or came back in, not sure. All right. What does at most mean? Let's think about that for a sec. At most 95. So it could be 95 or it could be less, right? So the claim from that statement is that the average is less than or equal to 95, right? That's at most. Since it has an equal to in it, this claim must be the null hypothesis. So the alternative hypothesis, we could call it H1 this time for fun, that would also be mu, and the opposite of that would be greater than. And remember, null hypothesis always has an equal or less than or equal to or greater than or equal to. An alternative can never have any kind of equal to in it. It's either less than, greater than, or just not equal. Since this is greater, that implies this is a right tail test, because greater than means look to the right. So I'm going to start my sketch here. So right in the middle, oops, sorry about that telephone ringing there. Mu is 95, goes in the middle always, and then we're looking to the right. And so somewhere out here is going to be my sample data. And the question is my sample data close enough to 95 to say, yeah, it's at most 95, or is it far enough away to say, whoa, ICU patients have a higher heart rate than this 95? And average heart rate of a healthy person, I think, ranges, if they're just chilling, ranges somewhere between like 60 beats per minute and like maybe 100 beats per minute. So 95 average is at the upper end of normal for people. And there's lots of things that affect heart rate, like whether you're an athlete, your age, other health things. So it's a pretty varied thing. So it's not as tight as, say, body temperature. All right, so now we got to look at the data, see what happens, find out a p-value, see how significant this is. All right, so which one do we want here? This is an average, right? So that means ignore anything with a p in it. At most meant less than or equal to, so that looks like this one right here. Mu is less than or equal to 95, that's at most 95, and there's my alternative. And they're using a little 1 instead of an A, which is fine. Okay, what else do we got? This is because of the alternative being greater than a right tail test. And then, oh, no, stop it. Page is freaking out. So now we go to StatKey and switch to the data set ICU admissions. So the data is already there. And I summarized the data for you. What you'll find there is a mean of 98.925. So I might as well throw that in my graph since I know it now. Red, yep, 98.925. Sample size matters too. So some people might say, 98, 99, that's pretty close to 95. For a single person, maybe, but for a mean, that could be very far away, depending on the sample size. And how many people do we have in this sample? 200 people. That's not huge, but it's considerable. So that the sample size n is 200 could mean that that's far away on average, right? We're not talking about an individual person here. This is super important. We're talking about the average of 200 people. So extremes get whittled down to the middle. All right, so let's go and run the test. Go, there we go. Switch, make sure you get the right data set, and I want ICU heart rate. Okay. They gave me a mean of 72, so that's the low end of average. So let's say that would be maybe somebody in their 20s or 30s, healthy. Average heart rate of people in their 20s and 30s is probably around 72 beats per minute. And a healthy person in their 50s, that group of people might have an average heart rate of around 72. As you get older, it goes up. All right, so we want to change that. That's the wrong one, right? We were told mu was 95. Don't forget to double check that you have the right data and the right null hypothesis. That this says equal to as opposed to less than, that doesn't matter. Bottom line is whether the null hypothesis is equal to, less than or equal to, or greater than or equal to, whatever that number is always in the middle of your distribution. That's what matters. Generate, generate, generate. 7,000, let's go 7,111. Let's be a little crazy today. And right tail. Okay, so they threw a number down here that puts 2.5% in the extreme there. We want our mean of 98.925 in there, so we gotta go adjust. 98.925, did I type that right? 98.925, I think so. That's right. Okay, so they say the probability of finding another sample of 200 people with an average heart rate greater than 98.925 is about 1.7% if we expect the average heart rate to be at most 95 beats per minute. Okay, so I'll write that down. That's the meaning of this p-value. And I do ask about that in the application, which hopefully will be posted this afternoon. I'm almost done editing it. All right, so p-value 0.017. So 1.7%, what was my significance level here? 5%, so that is less than the 5%, so that means, hey, this is significant. This is far enough away from 95 to say ICU patients have a higher heart rate than 95 beats per minute on average. Again, we're not talking about an individual. We're talking about a group of 200 people, whittle down all their information to a single number. That takes out the extremes because we're just pointing at the middle, the average. That's a tough thing to wrap one's mind around, I believe. So where's my sketch? Over here. All right, so again, I already marked my center, I marked my sample. 98 is greater than 95 because this is a right tail test. If you say it's a left tail test, but your data is on the other side, that's messed up. That should never happen. That means either you have the data wrong or you picked the wrong hypothesis. They always have to match. So we found that if we look for another sample of 200 people, the chance of finding such a sample where the mean is greater than 98.925 is about a 1.7% chance of happening. This is our p-value. And again, I'll interpret that in a minute too, because again, that interpretation is important and a bit tricky. Because this is small enough, right? This is less than the significance level I was given. And so let's see, the significance level is called alpha. And that's kind of an arbitrary number researchers throw out. Let's see, we were given 5%, which is kind of the default if you don't have another good idea. Okay. So our p-value is smaller. So if your p-value is small enough, then you get to reject the null and accept the alternative. So my decision is reject null hypothesis. And then we have to come up with what that's the decision. What's the conclusion? So the conclusion is something I would tell my mom. So I got to try and work that up. So before I go and push some buttons on the homework problem, I'm going to try to write it myself. I recommend you try to do the same. If you're feeling at a loss about how to write that up, then read those and try and write something in similar language. All right, so let's see. Based on the sample data, I could say, there is sufficient evidence to reject, and now we're not going to say reject the null hypothesis, because my mom's like, what the heck's the null hypothesis? We got to stay what it is. To reject the claim that the average, let's see, pulse rate, or heart rate, I guess they said this time, same thing, pulse rate of ICU patients is at most 95 beats per minute. And since we are rejecting, I'm going to go ahead and say what we're accepting. So let's see, we reject the claim that it's at most 95 beats per minute and accept that the mean heart rate, pulse rate, to be consistent with what I wrote the first time, is more than 95 beats per minute. Okay, so it should look something like that. So we just got to figure out from the selections I gave you which is the right one. So we do have a small p-value. It's less than the significance level, so that means we get to reject. And then there's a bunch of different wordings here. Some of these are false and some are nonsense. So the first one, based on the sample data, there is sufficient evidence to accept the claim that average heart rate is 95. Okay, no, that's not what we found. So definitely not the first one. Second one, based on the sample, there is sufficient evidence to reject the claim that the average heart rate of ICU patients is at most. Okay, so that's rejecting at most, which was my null hypothesis, so that starts off good. And accept the alternative claim that the average heart rate of ICU patients is greater than 95 beats per minute. Looks pretty damn close to what I wrote. Let's double check the other ones just in case. Based on the sample data, there is not sufficient evidence to reject the claim that average heart rate of ICU patients is at most 95. So no, we did find sufficient evidence, so that's wrong. And then the last one, based on the sample, there is sufficient evidence to reject the claim that the average heart rate of ICU patients is at most 95 beats per minute. Sorry about the background noise. And accept the alternative claim that the average heart rate of patients is, okay, we can never accept an alternative that something is, right? That's an equal to, we can never prove something's equal because we never have all of the data. And that's the sample value. We don't know the average is 98. The average of the population is 98.925 beats per minute. We don't know that. That's just this one sample. So this last one is crap. All right, it's got to be the second one. Check all my boxes. Let's get some green check marks. Woo! Did all right. Cool. So again, write those down. And so just reading something is significant, right? Our brains remember a lot of what we read, but our brains remember more of what we write. So write this yourself to help cement this kind of language in your head. Please, please, please do that. And again, every time you do one of these, draw pictures. So if you send me a question on a hypothesis test, I'm going to say, hey, can you show me your picture? And so this is what my picture looks like for this one. You should have a little bit of language saying this is what I'm attempting to measure and test, null, alternative, p-value drawn in the right place. Cool, making progress. Oh, I said I would talk about the interpretation of the p-value. Let's do that. What the hell does it mean, that 1.7%? All right, so when we ran this test, we were assuming the null hypothesis was true. We're assuming that average heart rate is at most. Anytime you run a hypothesis test, you're assuming the null is true. Okay, so maybe that ding dong is because somebody left the group. I think so. All right, so it looks like I get a note anytime someone enters or leaves the meeting. So do I have room to do that here? No, let's go over here. Okay, so what is a p-value? What does it mean? More specifically, what does this p-value mean? So the p-value comes from that drawing, and in that drawing, I assumed that I should get a mean of 95 beats per minute, but I got a mean that was greater. So that was X bar. And the p-value is related to finding other samples that are more extreme than the one we found. And we found that to be 1.7%. So there's a 1.7% chance of finding another sample with a mean higher than 98.925 when we were expecting the mean to be 95. That's what this p-value means. So there is a 1.7% chance of finding another sample and this was a big sample, right? There were 200 people, so another sample of 200 ICU patients. With an average heart rate that is higher or greater, whatever you like, than what we found, that 98.925 beats per minute. When we were expecting an average of 95 beats per minute. In the probability notation I used a couple of weeks ago, this is a conditional probability. So it's the probability of finding some sample with a mean that is higher than 98.925, given or knowing that the mean of the population should have been 95. Okay, so that's the probability notation. This is how I would explain it to the news, my mother, and that's the interpretation of the p-value. So just saying the p-value is 1.7%, that's just a statement. It doesn't have any meaning. This is its meaning here. It's a conditional probability. Okie doke. So let's see, those are the questions that popped up there. I wanted to go back and look at number 12 for a sec, just for fun. So number 12 is almost the same question, but there's a slightly different claim. So this time I want to test the claim that the average heart rate of ICU patients is greater than mu equals 75 beats per minute. So notice I was given a greater than here. So greater than, that must be an alternative hypothesis. So I'm just going to grab that on a new page and see what happens. New page, screenshot. So same data, different claim. And highlight the important stuff here. So right away, I have a mean and I have a greater there. So they're telling me mu is greater than 75 beats per minute. That's going to have to be the alternative hypothesis. So H1, oops, colon is the usual notation. Again, this is the alternative. And the null hypothesis could either be one of two things. The null hypothesis could just be, hey, mu is equal to 75, or we could go for the opposite of this, would be less than or equal to. 75 would be another option here for the null. I would usually go with the simpler one. Let's see, what else here? Quick sketch. So we put mu is 75 in the middle. This is a right tail test because of the greater than, because of the alternative hypothesis. So somewhere out here is my sample data. And then we run the test and see what happens, find a p-value. So as far as selecting the right one here, I want the alternative with the greater than, and it's got to be a mu, not a p. It's got to be that one. That greater than on the alternative means it is a right tail test. And then I already have the data over here. I just need to pick a different null hypothesis. And I was given 75. So double check you have the right number here for the null hypothesis before you generate. So I have the right data, right null, generate. Get at least 6,000, decide on your test, and then type in your value, 98.925, enter. That number is off the charts, holy crap. Okay, so if somebody came to you and said, I think the average heart rate of ICU patients is 75, but I get the sample that says the average is 98, right? They are so far apart, they're not even like in the same city, okay? So the p-value is pretty much 0, and that happens sometimes, okay? So this is my p-value right there, it's about 0. So my sketch is a little bit not quite right because that X bar should be way the hell out there, but that was my first drawing. So this is 98.925, and that p-value is essentially 0. Theoretically, it's a tiny little number, but StatKey couldn't handle it. 0. So there's no chance of finding a sample of 200 people with an average heart rate of 98 if it's true that the average heart rate should have been 75. So something's wrong. So either the sample is bad or the null hypothesis is crap, not true. So we're assuming we have a good random sample, which means the null hypothesis is flawed. So we must reject the null hypothesis here. Because given that this is supposed to be a good random sample, there's no chance of finding another sample of 200 that's greater if we expected the average to be 75. And sometimes that happens. The data is just way the heck out there, and that means the null hypothesis is likely incorrect. So filling this out some more, my p-value is essentially 0. 3 decimal places is still 0. We are definitely rejecting the null hypothesis because the p-value is so damn small. And then it's a matter of picking the right one here. Let's see, based on the sample data, there is not. No, we found evidence. So it's not the first one for me. And yours will be in a different order, by the way. It shuffles them every time it runs a problem. There is sufficient evidence to accept the claim that the average pulse rate is 75. No, it's way bigger than 75. How much bigger? I'd have to run a confidence interval to figure that out. So it must be this last one. Based on the sample, there is sufficient evidence to reject the claim that the average heart rate of ICU patients is 75 beats per minute and accept the alternative claim that the average heart rate of ICU patients is greater than 75. Yeah. I think we're pretty clear it's greater. Nice. All right, so the main reason I wanted to do this particular version of that problem is because sometimes people freak out when they see a p-value of 0. Don't freak out. It just means that the sample we got is, as provided it's a good sample, is just so far from what the null hypothesis was that we got to throw out the null hypothesis. All right, so that's it for today, unless you have further questions. Nothing's up in the chat at the moment. I highly recommend you try these again. Read in the book, they give a bunch of conclusions, and those are the harder thing to write. Like, what does it mean to reject the null in this situation? Interpreting the p-value is another tricky thing. Read about that in the book some more. And if you're still struggling with it, you're going to get to try it on the application and get some feedback. And I will certainly do more tomorrow of problems like this. I found some new data sets I'm going to look at tomorrow with you that are slightly different from the homework. All right, take care and do good math. I will see you in the near future.